Hi guys, so today we are going to be talking about one of Newton's 3 laws of motion, and obviously I'm going to do them in order because why not? The standard that covers this is 8.3. It says create a demonstration of an object in motion and describe the position, force, and direction of the object. So this standard correlates to Newton's first law, which is also known as the law of inertia. So let's take a peek, review the notes over that, and then we'll get into some questions. All right, so Newton's 3 laws of motion. This is the one that says an object in motion tends to stay in motion unless acted upon by an outside force, and an object at rest tends to stay at rest unless acted upon by an outside force. Now, most people know it with outside force, so we're going to switch it up with one of our vocabulary words, which is going to explain the outside force, which is an unbalanced force. If you've forgotten the difference between balanced and unbalanced forces, balanced forces will cancel each other out. So like 5 newtons to the left cancels out 5 newtons to the right. Unbalanced forces are literally what they say they are. They're unbalanced. So if I had 5 newtons to the right, but 10 newtons to the left, that 10 newtons will overpower the 5 newtons and that object is moving to the left. That's why it says the object in motion will stay in motion, so it's going to keep going in its direction or trajectory unless an unbalanced force knocks it out of that line of motion, just like an object at rest. Most of us are probably extremely grateful that objects at rest will stay at rest unless acted upon by an outside force, because if your TV, your lamp, your refrigerator, big heavy things and, important stuff to you just started wandering around your home or out the door or up on the ceiling or something obnoxious like that, we're going to be concerned and life's not going to go quite so well. So make sure you know the difference between balanced and unbalanced forces. Also, this law is known as the law of inertia. Now, since we are all wonderfully quarantined right now, we are way more familiar with the concept of inertia than you might think. Inertia, simply put, is an object's resistance to change, okay? And usually I say this in my classroom, it's like my first block students. They've woken up, they're still in sleep mode, they don't want to be in school, they're resistant to that change in their regularly scheduled program of, teenage apathy. It happens. Here in quarantine mode, we are all probably very comfortable with looking like a hot mess. Maybe like being in the same PJs for 3 days in a row. Maybe some of you haven't left a bathrobe. Your hairbrush has collected a thin film of dust. Just we've gotten to some new habits, and it's going to be a little upsetting to some of us when we have to change those again. So inertia should be a concept we're very familiar with. Now, not personifying inanimate objects or anything, but objects are resistant to change in motion. That's why you have to shove things to get them to move or pick them up and put them places. They don't just typically do that of their own free will. Again, that would be terrifying and creepy and probably extremely frustrating. So that's why it's referred to as the law of inertia. Objects want to keep doing what they're doing. On the same note, we talked about objects at rest having to be pushed or moved. Objects in motion keep wanting to go in the direction of motion they are going. Take a car, for example. When you have a car going down a highway, it wants to keep going in that direction. It's going to take a substantial amount of force to move it from its trajectory. And again, I'm talking about an outside force, not gently turning the steering wheel. So this is why we refer to it as the law of inertia and how that vocabulary word plays into this. And again, I have a whole slide on here. Resistance to a change in motion. That includes being at zero motion, just sitting there at rest. That's why the law covers an object in motion and an object at rest. We cover all the bases here. So got a couple examples we can take a peek at. Moving objects want to continue moving, like your body when someone slams on the brakes in a car. We all have that lovely driver in our lives or family that has the habit of brake checking people and not warning the passengers in the car. So those of you that have your heads down, totally bent into your cell phone, and then all of a sudden seatbelt is trying to, kill you, because they brake checked someone. Whatever speed the car was moving when they slammed on their brakes, your body is still traveling at that speed. That's why it's super important for you to wear your seatbelt, because in the unfortunate incident of a car accident, if you do not have your seatbelt, and God forbid that car accident happens at about 70 miles per hour or more, your body is going to hurtle 70 miles per hour or more through that windshield until that object in motion, your body, meets an unbalanced force that causes it to stop rather painfully. So that's why seatbelts are important, children. Example 2. Stationary objects want to remain at rest, like a soccer ball. It's just going to sit there until someone kicks it, because let's face it, soccer would be a horrifically boring sport if we just all stood on the field and waited for the ball to score itself into the goal. Ain't gonna happen. So, yeah, there's your first law of motion with inertia. Now, key concepts here. Inertia and mass are super closely linked together. Now, mass and weight are not the same. That's a different standard I'll fuss about later, but again, just trying to clarify, mass and weight are not the same. When we speak, we use the words interchangeably, and we really, really shouldn't. Mass is the amount of matter in an object, okay? So this should make complete and total perfect sense. The more mass something has, the more force it's going to take to change its motion. That means the more massive it is, the more inertia it's going to have. It's going to be a lot easier to pick up like your pet hamster and move it somewhere than like an elephant, okay? So more mass an object has, the greater its tendency to resist a change in its state of motion. Galileo Galilei, he was the one that stated it was just as natural for an object to be in motion as it was to be at rest. I think we have a habit of, when we think of an object's natural state, we think about it just sitting there at rest doing nothing until we start making it active or some unbalanced force does. And this isn't necessarily true. This is an assumption that we have. So think about the planets in our solar system. They are naturally in motion. That is their natural state. Our moon around our planet is naturally in motion to continue orbiting. So keep in mind, it's just as natural for an object to be at rest as it is in motion. So going back to balanced and unbalanced forces, if the forces are balanced, meaning they're canceling each other out, their net force, which is the total force of all the forces acting on an object, is going to be 0. So you can kind of think about it like integers in math. If that 5 newtons from one side is positive and the 5 newtons from the other side is negative, when they meet, a positive 5 and a negative 5 equal 0. They cancel each other out. Okay, this applies to moving objects as well. An unbalanced force is not necessary to keep an object in motion. And an object does not come to a rest position due to an absence of force. It comes to a rest position because of the presence of a force. And that force is most likely friction. If you doubt this, most of you have had the unpleasant experience of royally wiping out at some point on a gym floor and having that lovely like skirt noise as the lovely polished gym floor grinds your poor defenseless skin to a literal screeching halt. That is friction. Friction works in the opposite direction of motion, which is why it typically brings things to a screeching halt. Same thing with like carpet burn and road rash. That's friction at work for you. So again, literally what I just said, friction moves in the opposite direction of motion. You got static, sliding, and rolling. I'm not going to worry about those too much because this video is getting long enough as it is. And big key concept here, since it's moving in the opposite direction of motion, it is never going to speed anything up, okay? And without friction, which we are eternally grateful for, whether you realize it or not, objects would move forever in a straight line until acted upon by an unbalanced force. This is the reason why when you like push a ball and it eventually stops rolling, That is thanks to friction. If there was no friction, then all of the objects in your home would most likely still be moving and sliding across the floor right now because there was some type of mild force in a direction whenever you place them there. So we are grateful for friction. It's also one of the reasons why brakes will work on a car too. We can look at a couple of objects here and describe some of the forces acting on them. So we've got an object at rest, which is going to be lovely, happy newscaster here, object number 1. And we have an object in motion, which is our lovely alien-seeking Naruto runner. Some forces, they're both subject to gravity. Neither of them are floating, which would, since we're talking about aliens here with Area 51 raid, that would make this a little bit creepier. Neither of them are floating, okay? Looking at his hair right here, I would say that both of them have some type of wind resistance on them. Okay, there are some forces acting on each of them. Balanced and unbalanced forces. Unbalanced forces, he is obviously moving forward. So the force of him moving forward is going to be greater than the force of wind or air resistance against him. So we've got several forces at play here. And then last but not least, a free body diagram. I'll just briefly kind of show you one here if I can sketch it out real quick. Alrighty, so we have a force pulling down on him, which is going to obviously be gravity. We have the null force, which is his body pushing on the earth, balancing out. It's the reason why gravity's not crushing him. So we have our normal force. He is running the air. So we have air resistance here going against him. And then, of course, we have that his body is exerting to push him forward. So these are going to be an example of free body diagrams. If you wanted to put some numbers in here, the force of gravity, I believe it's 0.91 newtons. It's been a while since I've looked at that number, so it may be off a little bit, which means the normal force will also have to be 9.1. Ooh, that one got a little wonky. Newtons. Air resistance, we can literally give some type of random arbitrary number. We'll say the wind is blowing at a lovely 1.2 newtons. And since he is moving in the opposite direction of air resistance, let's say his body is generating a force of, I don't know, we'll just put 12 newtons. So notice how I made and this one number. These are balanced forces, so they have to be the same to cancel each other out. I made these two different numbers because they're unbalanced forces, which is the reason why he is moving to the right. And if it helps you to figure out what are balanced and unbalanced forces, since I'm right-handed, anything that is moving to the right, I usually associate as positive. Anything moving to the left, I associate as negative. Just like anything moving up, I'll associate as positive, whereas something moving down, I will associate as negative. So if you add those two together, they equal 0, which is why they're balanced. If you add these two together, you get a sum. So whichever direction, if it ends up being positive, this one wins, so it's moving to the right. If it ends up being negative, this one wins, so it's moving to the left. That's just how I've done free body diagrams in the past, and it's helped me in physics classes to help sketch anything out. And that's honestly one of the #1 pieces of advice I can give you in just about any physics class, is if you can draw it, draw it.